Then she pursued her master's degree in thermoplastic elastoma and graduated on 2014. She was successfully graduated on time, GOT, and earned her PhD in hybrid polymer composites in 2017. Dr. Nick Noridayo was awarded with Excellence Research Award for her tremendous achievement in her PhD at the 87th Convocation Ceremony, which was held in UITM Shah Alam in October 2017. Dr. Nick Noridayo currently serves UITM as a fellow researcher in Center for Chemical Synthesis and Polymer Technology, Institute of Science, UITM. Apart from that, she is also a senior lecturer in Faculty of Applied Science, UITM Shah Alam. Dr. Nick had secured many research grants. She had also attended national and international conferences, invention and innovation competitions. She had published various publications, especially in polymer composites. Ladies and gentlemen, please welcome Dr. Nick Noridayo binti Nick Ibrahim to give us a talk on solid lubricant ultra-high molecular weight polyethylene micro-bearing concept. Dr. Nick, the screen is yours.
Okay, Assalamualaikum and good morning. Today I am going to share a bit on one of my research entitled Solid Lubricants Ultra-High Molecular Weight Polyethylenes Micro-Bearing Concept. So my name is Nick Noridayo Ibrahim from Center for Chemical Synthesis and Polymer Technology, Institute of Science, UITM. So this is actually a project done by my master student, Ahmad bin Arifin, which is supervised by Dr. Ahmad Zafir Romli, the head of a Polymer Composite Technology Group, and I'm co-supervising this project. Okay, for the outline for this sharing sessions will consist of introductions, concept, methodology, result and discussions, and the last one is conclusions. Okay, before we go further into the topics, let's take a look a bit into what is bearing and friction. Okay, a bearing is a machine's element that constrains relative motions to only the desired motions and reduces frictions between moving parts. So the designs of the bearing may, for example, provide for free linear movement of the moving part or free rotations around a fixed axis, or it may prevent motions by controlling the vectors or normal forces that bear on that certain moving parts. So most bearings facilitate the desired motions by minimizing frictions. So bearing, in fact, are so fundamental to the machines industry that they have been called the industry bread and butter because they are used in all sorts of machines. So there are two major functions of bearing, which is the first one is reducing frictions and making movement smoother. Frictions is bound to occur between the moving shaft and the part that support the movement. So the bearing serves to reduce frictions and allow for smoother movement, and this will cut down on the amount of energy consumption. So the second one is protecting the part that support the movements and maintaining the correct positions of the moving shaft. Normally, a large amount of force is needed between the moving shaft and the part that support the movement. So the bearing will perform the functions of preventing damage from being done by this force to the part that support the movement, and also of maintaining the correct positions of the moving shaft. Okay. Next is friction is a fact of life. So rolling, rotating, and sliding contact interfaces in every human-made, natural, or biological system will generate frictions. If not reduced or controlled effectively, excess frictions often leads to higher wear losses and ultimately poor reliability and lifespan. So frictions, most basic definitions is the force that prevents smooth and easy movements of two moving surfaces in contact with each other. With frictions comes wear and tear, and thus lubricants in a liquid or solid forms are needed to prevent this or to minimize the frictions. A proper lubricants will reduce frictions between the internal sliding surfaces of the bearing components. On the macro scale, Frictions is the result of microscopic imperfections in surfaces. So on the atomic scale, however, frictions concern the attractive forces between individual atoms. According to the Fluid Power World magazine, I quote, the design engineers have long searched for material sorting method to reduce frictions, but could the restructurings of newly found material reduce frictions on microscopic scales? So when industry and academia began searching for a material with self-lubricating properties that can be applied on any surface, graphene has come into the picture. So with graphene being two-dimensional material, it offers unique frictions and wear properties that are typically not seen conventionally. But what the most important is, graphene can be used as a solid lubricant. Solid lubricants are also known as dry lubricants. By definition, is materials that, despite being in the solid phase, are able to reduce frictions between two surfaces sliding against each other without the need for a liquid oil medium. So the most common material used for solid lubricants, including graphite, molybdenum disulfide, hexagonal boronitride, and tungsten disulfide. Solid lubricant finds its applications in various fields. One of them is in arthroplasty. So arthroplasty is basically a surgical procedure to restore the functions of a joint, especially on hip and knee, which is normally known as a total knee arthroplasty and total hip arthroplasty. So the most common material used for these kinds of implants, including stainless steel, cobalt chromium alloy, titaniums and titanium alloy, uncemented implants, tantalums. Tantalum is a type of pure metal, zirconiums, and also polyethylene. For polyethylenes, there are a few types, which is the ones that is used as a solid lubricant is ultra-high molecular weight polyethylene, which has been the gold standard for orthopedic joints for over 40 years after its introduction, due to the combinations of superior wear resistance along with high fracture toughness and biocompatibility compared to other polymers. So if your knee or hip have been damaged by arthritis, fracture, or any other conditions, common activities such as walking, climbing stairs, or getting in and out of a chair may be painful and difficult. So total knee replacement and total hip replacements are normally a last resort when it comes to a damaged knee or hip. So prior to invasive surgery, doctors will recommend everything from physical therapy to stem cell treatments in order to see if a hip or knee replacement can be avoided. But for some patients, however, simply have too much wear and tear on a hip or knee. So in this case, if non-surgical treatments like medications and using walking support are no longer helpful, total knee or hip replacement surgery is something to consider. Okay? This is the picture of anatomy of normal knee and normal hip. Knee is actually the largest joint in the body, and having healthy knees is required to perform most everyday activities. In a healthy knee, these structures work together to ensure smooth natural functions and movement. So the knee is made up of the lower ends of the thigh bone, which is the femur, the upper ends of the shin bone, which is the tibia, and the kneecap patella. So the ends of these three bones are covered with articular cartilage, which is a smooth substance called tissue that protects the bones and enables them to move easily within the joints. Okay? Similar to the knee, hip is also one of the body's largest joint. It is a ball and socket joint. The socket is formed by the acetabulum, which is part of the pelvis bone. And the ball is the femoral head, which is the upper ends of the femur thigh bone. And the surfaces of the femoral head and socket are also covered with articular cartilage that cushions the ends of the bones and enables them to move easily. Right. The most common cause of chronic hip pains and knee pains is arthritis, which is osteoarthritis, rheumatoid arthritis and traumatic arthritis are the most common forms of this disease. Okay? Osteoarthritis is an age-related wear and tear types of arthritis. It usually occurs in people 50 years of age and older, but may also occur in younger people. So the cartilage that cushion the bones of the knee and hips soften and wears away, causing the bones to rub against each other, leading to the pains and stiffness. Rheumatoid arthritis is an autoimmune disease in which the synovial membranes that surrounds the joint becomes inflamed and thickened. So these chronic inflammations can damage the cartilage and eventually cause the cartilage loss, pains, and stiffness. So rheumatoid arthritis is the most common forms of the group of disorder termed inflammatory arthritis. Okay, the third one is post-traumatic arthritis, which is normally happen due to a serious knee or hip injury. So fractures of the bone surrounding the knee or hip or tear of the knee ligaments may damage the articular cartilage over time, causing pains and stiffness and limiting the functions. So as you can see in this picture, the damage is normally occur to the articular cartilage where it is worn out and no longer able to keep the bones at a normal distance apart. So as a result of our body attempt to repair the loss of cartilage, bone spur is normally occur near the damaged area. The number of knee joint replacement operations performed each year is rising steadily, and experts estimate that around 2 million knee replacements are implanted every year. So as a result, knee replacement is the most frequently performed joint replacement, even taking precedence over hip replacement surgery. Okay, there are a number of hip and knee implant devices available in the market, produced by different manufacturers and constructed in different model types. The materials used are also varied, but the most popular used materials are metal, plastic, and ceramic. These materials are used in combinations and are mostly seems to fall into one of these three basic categories, which are metals on plastic, metal on metal, and ceramic on metal or ceramic on plastic. Okay, for metal, stainless steel is normally more suited to being used as a temporary implant, such as fracture plates and screws, due to its limited ability to withstand corrosions in the human body. However, one area of concern when using metal is the releasing of metal ions, such as nickel, into the bloodstream that would subsequently lead to many health issues, including kidney disease and neurological damage, especially for those with a metal allergy. So compared to metal, ceramic implants seems to be promising for patients with allergic against metallic implants material. So the high performance ceramics are biocompatible and bioinert and does not elicit any non-allergic reactions. However, due to its hard and brittle behavior, it has a risk of fracture and crack. Okay. For plastic, ultra-high molecular weight polyethylenes and cross-linked PE are usually used for implants due to its better durability, non-toxic, proven long-term success result, and also has better toughness that suit people of different lifestyles. However, it also wears out over time, causing inflammation and bone loss requiring for a revision surgery. The life expectancy of the world's population is higher now than ever before, as such that the request for greater mobility and improved quality of life following knee replacement has also increased. So the incidence of knee replacement in young and active patients is also increasing, and therefore knee replacement must be able to offer longer implant lifetimes. So in addition to this, infections, polyethylene wear, implant loosening, and metal allergies are among the greatest problems in knee arthroplasty. Aseptic loosening is the predominant mechanism in failure and revisions, followed by instability, infections, polyethylene wear, arthrofibrosis, and malalignments. So this is why the choice of implant material is so important, especially with respect to the wear properties and biological behavior of the selected materials. Next is for the research concept. Okay, the main principle for this research is the micro-bearing concept. Ultra-high molecular weight polyethylene has been used as a bearing material in a total joint arthroplasty for more than 50 years now. So the idea to replace the degraded cartilage with the polymer liner dates back to the late 1950s. So at that time, Sir John Chanley chose polytetrafluoroethylene, PTFE, which is a low-friction polymer as the bearing materials to replace the natural acetabulums, articulating against a metallic femoral head for hip replacement. However, due to the overly low wear resistance of PTFE, it is dramatically failed after a few years of implantation. So in 1962, ultra-high molecular weight PE comes into the picture. A similarly low frictions but much more wear-resistant polymer with remarkably better performances. So from then on, arthroplasty has known considerable evolutions, but ultra-high molecular weight PE remains the gold standard for artificial hips, knee, and shoulder. However, it has been demonstrated that the main factor responsible for the failure of ultra-high molecular weight PE in joint replacement is oxidative degradation, which decreases its mechanical properties, including the abrasive wear resistance. This leads to the formations of wear debris and consequently to osteolysis, which has been recognized as being the main cause of failure in orthopedic implants. So orthopedic components must undergo sterilizations before clinical use. When ultra-high molecular weight PE is exposed to a stronger energy than that of the chemical bond, the consequence is bond scission and the formations of free radical. So this change fragmentations modifies the mechanical properties of the polymer itself. So being exposed to the high energy gamma radiations during this sterilization process, it can have a detrimental effect on the morphology and mechanical properties of ultra-high molecular weight PE due to the continuing change season and long-term oxidative degradation. So macroscopic evidence for the oxidative degradations caused by gamma sterilizations in air can be seen on this figure A, where it looks like a white halo and it is called the crown effects or white band. So this is a zone where a critical molecular mass decrease has occurred and which therefore has a very low mechanical properties, resulting in the well-known effect of delaminations and fracture that are typical of such components. So figure B and figure C shows the fracture surface, and figure D shows the delaminations on the inside surface which occurred over time. Okay. So in this study, the main principle of micro-bearing concept can be applied as the micro-scale ultra-high molecular weight PE filler in the form of a tiny bit particles, which is deposited on the surface of the epoxy composite. So due to the difference in density of the epoxy and ultra-high molecular weight PE leads to the formations of layers that act as the lubricating materials to resist the frictional force exerted onto the composite system. So this micro-bearing concept involves the fundamental study of materials rheology, which including the non-Newtonian squeezing behavior of polymer as relations to the viscosity and density. So when the ultra-high molecular weight PE filler was incorporated into the epoxy resin, the situations where the density of epoxy resin, which is about 1.12 gram per centimeter cubic, is higher than the density of ultra-high molecular weight PE, which is around 0.92 gram per centimeter cubic, will encourage the microparticles of ultra-high molecular weight PE to accelerate upwards and floating until it is partially submerged during processing before it undergoes curing process, forming two distinctive layers. So upon curing of the polymer composite, the ultra-high molecular weight PE filler will be turned into a layer of solid lubricants on top of the epoxy composite systems. However, other than the density of the components, there are several other factors that will influence the concept, especially upon increasing amounts of filler loading in the epoxy resin. So in plastic materials, the incorporations of a short filler will increase the viscosity of the polymer mixture. This will lead to the dilatant behavior, which is the shear thickening of the non-Newtonian fluid upon increases in the shear rate, which first described by Einstein equations. So due to that, the need of a diluent is important in this study to lower the viscosity of the epoxy resin so that the ultra-high molecular weight PE particles are able to move upward within the working time range. So as for the diluents, acetone solvent is used, which has been widely used by various studies to improve the processing parameters and behavior of respective fillers inside the matrix constituent. So for this study, epoxy was chosen as the matrix because epoxy, once fully cross-linked, is an inert material and mechanically stable. So epoxy has been widely used as a coating for metallic orthopedic devices such as prosthetic joints and dental implants made from titanium. Okay, for the methodology. Okay. After so many try and error and preliminary study on the method, this can be said the Optimus method, which involves a mechanical stirring of the epoxy and ultra-high molecular weight mixture, followed by the sonications to further improve the dispersions and breaking down the agglomerated particles. Then the additions of acetone to lower the viscosity of the epoxy resin, and lastly, the additions of hardener to initiate the curing process. Next, the mixture was put into the mold, left for cure at room temperature for 24 hours before post-cure in oven at 50 degrees C for another 24 hours. Okay, this is just the summarize of method. Okay, this is the final formulations. There is only one variable, which is the amount of ultra-high molecular weight PE varies at 1, 3, 5, 7, and 10%. So the optimal ratio of acetone was kept constant at 1:2 ratio of acetone to epoxy resin. The testing involved for this part are wear test, hardness, and coefficients of friction test, which is still in progress. Okay, for the result and discussion. Okay, this is the plotted graph of wear test result and hardness test result. Wear test result was conducted at 6 Newton load and 10 cm sliding distance for 3 hours using stainless steel pin according to ASTM G13296. So the result of a specific wear rate was plotted against increasing percentage of filler loading. So as can be seen from the graph, the specific wear rate of neat epoxy is about 7 times 10 to the power of negative 5 millimeter square per Newton meter. So the incorporations of 1 weight percent of ultra-high molecular weight PE has reduced about 53% of the wear rates of the composite. So as the amount of PE filler, ultra-high PE filler increased from 1 weight percent to 3 weight percent and 5 weight percent, the specific wear rate shows a small gradual reduction trend with 7% and 6% respectively. For 7% and 10% filler loading for these two, the reductions in the value of specific wear rate are quite obvious. When the filler loading increased from 5 to 7, there is a 36% reductions in wear rate. So as the filler loading was further increased from 7 to 10%, 50% reduction in wear rate was observed. For hardness test, the result was expressed in Rockwell hardness value against increasing percentage of filler loading. So the hardness test was carried out using 60 Newton major load 5-second delay times according to ASTM D785. So the incorporations of ultra-high molecular weight PE filler into the epoxy seems to reduce the hardness since the hardness of all filled composite is lower than the pristine epoxy. However, there is a gradual increasing pattern observed from 1% to 5% filler. So as the loading was increased to 7 and 10%, the hardness value seems to decrease. Okay, the relations between trend observed for wear test result and hardness test result can be explained by the concept of microbearing layer formed by the ultra-high molecular weight PE in epoxy system. Okay. The incorporations of ultra-high molecular weight PE in the epoxy system seems to produce two distinctive layers, which can be seen from this figure 1, which is taken from lateral view under polarized optical microscope at 5 times magnification. This is as predicted due to the difference in density of epoxy and ultra-high molecular weight PE assisted by the reduction in viscosity of the epoxy resin by acetone. So in figure 2, we can see that there are certain smooth areas which are corresponding to the ultra-high molecular weight PE particles. So from the result of wear test and hardness test, two possible conditions could be derived depending on the amount of filler loading, which is based on the graph. Filler loading at 1, 3, and 5 weight percent can be categorized as low filler loading. On the other hand, 7 and 10 weight percent can be classified as high filler loading. Okay. For low filler loading, the depositions of ultra-high molecular weight PE particles on the epoxy surface seems to be encapsulated by a thin layer of epoxy as illustrated in figure 3. So the presence of this thin layer of epoxy contributes to the increasing of hardness value up to 5 weight percent filler loading due to the stiffness of the epoxy itself. However, despite of the presence of this encapsulating layer, the low coefficient of frictions of ultra-high molecular weight PE still can be disseminated to the composite surface, which is observed directly by the gradual reduction in specific wear rate by this graph. So on the other hand, the encapsulating layer of epoxy seems to not be the case for the high filler loading composite, where the filler-filler interaction seems to be dominant compared to filler-metric interactions, whereby the cluster of ultra-high molecular weight PE are formed. So with all these clusters pushing to form the top layer, at the same time, they push away the vicinity epoxy resin, causing lack of resin layer on the top surface as illustrated in this figure 4. So when subjected to hardness testing, the value slightly decreased due to the exposed regions of ultra-high molecular weight PE, which possess lower hardness compared to epoxy. However, from the aspect of a specific wear rate, the exposed regions of ultra-high molecular weight PE contributes in reducing the specific wear rate by lowering the frictions between the composite surface and the steel pin. For the coefficients of friction test is still in progress and got a bit delayed due to this COVID pandemic. However, based on the result of wear test and hardness test, the coefficients of friction is expected to show similar trends to wear test, where the coefficients of friction decrease with increasing filler loading, with more apparent reductions observed for 7 and 10% filler sample. Okay, lastly, for the conclusions, ultra-high molecular weight PE microbearing concept in epoxy composite has a potential to be developed as the implant materials due to the strength of the epoxy and low coefficients of frictions and the high wear resistance of ultra-high molecular weight PE. So the incorporations of ultra-high molecular weight PE inside the epoxy resin seems to reduce the frictions on the composite surface by forming a layer of solid lubricants on top. However, this project still has a very long way to go. Detailed study and analysis need to be done on the effects of the materials to the human health. Besides of as the implant material, this microbearing concept composite can also be developed for other applications, such as for the sliding rail for door and window. And this concept will probably eliminate the usage of roller or a grease to reduce the friction. Alright, that is all for my sharing today. Thank you.
you, Dr. Nick, for a very informative presentation. So now I believe that we need to take a good care of our knee, joints, and hip. Get enough calcium so that we are not end up wearing a plastic knee, isn't it, Dr. Nick? Okay, now we will have a Q&A session. Let me see if you have questions. Okay, you can just type it in the chat box and I'll read it for you, all right? Okay, while waiting for the question, Dr. Nick, I actually have two doubts in mind. As far as I know, epoxy is largely used in paints, coatings, and adhesives for finishing and for like building and construction. So, is there any possible effect if we use epoxy in human body, like what you plan to do?
All right. Thank you, Puan Zainathul. Okay, epoxy, once fully cured, is a hard and inert material, which is also available in food and drug administrative medical grade. Okay, so epoxy has been used as a coating for medical devices such as prosthetic joint and dental implants. These prosthetic joints and dental implants are normally made from titanium due to its lightness, good mechanochemicals, and osteointegrative properties, make it an ideal material for bone implant applications. However, titanium implants have the risk of the risk of biomaterial associated infection, which is feared complications in orthopedic and trauma surgery with the tremendous consequences for the patient itself. In order to prevent infections of medical devices, they have developed an epoxy coating on this implant. So some of it even incorporated some antibacterial in the epoxy coating. So regarding the questions on the usage of epoxy in human body, I'm not going to say that it is 100% safe. Same with other materials. They have their own pros and cons. So and they also have their service life, right? So different person will react differently to the foreign materials in the body. People have different allergies, different lifestyle. So there are many factors that will influence how this material affecting our body. But basically, there have been some applications of epoxy in human body for certain parts.
All right. Okay. At the moment, you have already conducted, if I'm not mistaken, hardness and wear tests, right? So, what are the tests needed to be done, and what are the future plans for this project? And since your project involves something to be incorporated in human body, so do you have any collaboration with medical institutions?
So since the main target for this study is for medical material, so it is vital to ensure that the project safety and meeting the requirements of the highly regulated medical industry. But it is not easy to develop material for implant because it involves human factors. So you need to go through a strict board meeting ethics, you need to pass on certain level of testing and so many more. And we are still in the first stage of study actually, so we still have a very long way to go. Lots of tests that need to be done, including maybe trace elements analysis, liquid penetrant inspection, stress rupture, compression test, and few others. For the time being, we do not have any collaboration with any medical institutions because for this stage, we actually try to find the Optimus method first. So we try to get the two distinctive layers of epoxy and ultra-high molecular weight PE on top. So in theory, based on density, it is possible to get the two layers, but in reality, it is quite difficult because it involves other factors such as viscosity and dilatance behavior of epoxy itself. But then we get the optimized method after so many trials. So maybe for further study, we will collaborate with a medical faculty or medical institutions to see if these materials can go far. But for currently, we have a collaboration with the Kuliah of Medicine UAE, but that is not actually for this project lah. It's for another project. Me and Dr. Ahmad Zafir are designing a device to assist labor and baby delivery.
Okay, I see. And let me check if there's any room. Yes, yeah, there is no questions. So if you have any questions or doubt or any comment, you can just write an email to Dr. Nick Noridayo, and I pasted the email address in the chat room. So thank you so much, Dr. Nick, for a very detailed explanation. I believe we have again some new knowledge today. And again, if you wish to address any question, just email Dr. Nick, and the email has been attached to the chat box. And don't forget to click on the attendance list, attendance link given in the chat room for your jam latihan. Okay, thank you again for staying with us today. Till then, stay safe, stay at home, kita jaga kita. Assalamualaikum.